In this video, we will discuss about various built-in data types available in Python programming language. First of all, uh, irrespective of programming language being discussed, internal representation of any quantity is always in binary. The quantities are stored always in binary format. Only interpretation makes it integer, real number, or character, etc. It means any bit pattern, it can be interpreted as either integer or a character or a real number or any user defined data type. And this depends on the number of bytes used and method used to access the memory. What are the basic data types, built-in data types in Python? First thing, we should always remember that there is no reserved keyword for any data type. So user cannot declare a variable of type integer or real number or complex number, etc. But these are the basic built-in data types: integers, real numbers, complex numbers, sequence, a sequence type of data types, mapping, set, binary, strings, and booleans. Regarding strings and booleans, I've already made one video earlier, which is available on YouTube. Today we'll see how integers and real numbers and what is the role of complex numbers, and corresponding to all these data types I'll be making video subsequently. The restriction is the size of. What are the restrictions? Practically there is no limit on number of digits in an integer. So integer can be of any size. Practically there is no limit, but there is upper limit. We'll discuss this later. What are the ranges? By default, integers are signed. It means we can represent both positive and negative numbers. If an integer is of 2 bytes, we can represent numbers from integers from minus 32,768 through plus 32,767 or minus 2 to the power 15 through 2 to the power 15 minus 1. If it is of 4 bytes, this is the range, or you can say 2 to the power minus 2 to the power 31 through 2 to the power 31 minus 1. If it is of 8 bytes, this, or minus 2 to the power 63 through 2 to the power 63 minus 1. And real numbers. Real numbers, there are two ways of representing: fixed point and floating point. So using 2's complement, it is possible to represent numbers on both sides of 0 on the number line. For example, assume a fixed binary point. It is also possible to represent numbers with fractional component. So here is an example. For example, if my binary number is 10 point, this is binary point, 01. So 10.01. We know that in normal binary number to decimal, this place carries a weight of 2 to the power 0. This is 2 to the power 1. And if we move towards left hand side, the exponent increases. So 2 to the power 2, 2 to the power 3, 2 to the power 4, etc. Whereas after binary point, it increases in negative value. It means right hand side 2 to the power minus 1, 2 to the power minus 2. These are the weights. So how to make this number? This is 0 multiplied by 2 to the power 0, that is 0. Then this is 1 multiplied by 2 to the power 1, which is 2. So 2 plus 0, this makes 2, this 2 integral part. And after binary point, this is 0 multiplied by 2 to the power minus 1, the result is 0. And here 1 multiplied by 2 to the power minus 2, which is 1 by 4, which is nothing but 0.25. Add these two, it becomes 0.25. So final result is 2.25. So what is the limitation in this representation? very large numbers or very small fractions cannot be represented. So for real numbers, scientific notation or floating point representation is used. It has the advantage. What is the advantage? For example, I need to represent 4,56,000. This can be represented using 456 multiplied by 10 power 3. And if I want to represent 0.456, then it can be written as 456 multiplied by 10 power minus 3. What has been done here? The decimal point has been shifted to a convenient location. And exponent of 10, which is minus 3 here and plus 3 here. So the location and the exponent of 10 is used to track this decimal point. And that is why floating point. It is something like we used to do in slide rules. In slide rules, what used to happen is if you performed a calculation, then the pointer would remain at one place indicating 10 power 1 also, 10 power 2 also, 10 power 3, etc. So you need to estimate the correct exponent value. We can represent with this notation, we can represent very large as well as very small numbers using only a few digits. It can be applied to binary numbers also, as in computers, the numbers are always stored in binary format. Generally, we can represent a number as this: plus minus m multiplied by r to the power plus minus e. M stands for mantissa or significant, r is radix or base, and e is the exponent. So base is implicit and it is same for all numbers on a machine. So that is why it is not stored separately. So this representation can be stored in a binary word. So here suppose it is a 32-bit binary word. So bit 0 in this diagram, bit 0, it is sign of the mantissa. Bit 0, sign of the mantissa. Bits 1 through 8, these 8 bits, they represent the biased exponent, and bits 9 through 31, they represent the mantissa itself. So bit 0, sign of the mantissa, bits 9 through 31 mantissa itself, and bits 1 through 8 biased exponent. If sign bit is 0, then mantissa is positive, else negative. In case of exponent, a fixed called the bias is subtracted from the field to obtain the correct exponent value. Now 8 bits of exponent yield numbers 0 through 255. Of course, all bits 0, the number is 0. All bits 1, number is 255. So with a bias of 128, the correct values of exponent would be in the range minus 128 to plus 127. The base is of course assumed to be 2. Generally, real numbers are normalized. A normalized number is written in this form: plus minus 0 point, it is a binary point, 1 b b b b and so many b's multiplied by 2 to the power plus minus e. So b is a binary digit, 0 or 1. 2 is the base, of course, radix, and plus minus e is the exponent. Now in case of normalized representation, the leftmost bit of the mantissa has to be 1 always. So here it has to be 1 always. So when we know that it has to be 1, it is unnecessary to store it separately. And hence, in this way, 23-bit mantissa field has 24-bit mantissa. So we store 24-bit of mantissa in 23-bit mantissa field with a value between 0.5 and 1.0. In such a 32-bit format, following floating point numbers can be represented. Negative numbers between minus 1, 1 minus 2 to the power minus 24 multiplied by 2 to the power 127 and minus 0.5 multiplied by 2 to the power minus 128. These numbers, negative numbers, can be represented. Positive numbers can be represented which are between these two. Quite big number. 0.5 multiplied by 2 to the power minus 128 and 1 minus 2 to the power minus 24 multiplied by 2 to the power 127. But remember, still we are representing 2 to the power 32, that is approximately 4 GB kind of memory. If memory I am talking about, then 2 to the power 32 is 4 GB. So those many numbers we can represent. So we are still representing 2 to the power 32 numbers as word size is 32 bits. So approximately half numbers are negative and half numbers are positive. There is a property. As we move near center of the number line, the represented numbers come closer. And as we move farther away, the represented numbers spread farther apart. What does this mean? This means when you want to represent those numbers which are near to 0, that is the center, those numbers would be represented exactly. So numbers whose representation is exact, those numbers are more in number near 0. And as we move away from 0, that is the center point of the number line, the number of numbers which can be represented exactly become less and less. So between two numbers, the number of exactly representable numbers would be less. And that is why I always maintain that do not rely on the results of floating point operations, as not all numbers can be represented. Not all numbers can be represented exactly. Okay? Not all numbers can be represented exactly. So don't rely on these floating point computations. The following ranges are not representable in this format. So negative numbers which are less than minus 1 minus 2 to the power minus 24, this is known as negative overflow. Negative underflow, the negative numbers which are greater than minus 0.5 multiplied by 2 to the power minus 128. Positive underflow, positive numbers less than 0.5 multiplied by 2 to the power minus 128. Positive overflow, any positive number greater than 1 minus 2 to the power minus 24 multiplied by 2 to the power 127. And in all practical systems, there is a special bit pattern to represent this value, which is known as 0. Now, for sophisticated numerically oriented programs, the Institute of Electrical and Electronics Engineers, IEEE, developed in 1985 what? IEEE 754 standard. This standard was made to make the representation independent of the hardware to ensure the portability. This is widely accepted and adopted, and in most modern processors and coprocessors this is used. The standard 754 defines both single precision, that is for 32-bit, and double precision, that is 64-bit formats. Both formats have bit 0 as sign bit. It has 8 bits, that is for 32 bits, and 11 bits exponent for 64-bit representation. The base is of course assumed to be 2. This standard defines two more extended formats. Two extended formats, one is single and another is double. So it means single extended and double extended. And these extended formats have extra bits in mantissa field and exponent field for improving precision as well as the range. But in any case, exact format is implementation dependent. So this is IEEE 754 standard properties. So this is parameter number of bits in single precision, 32 bits. In double precision, 64 bits. In case of single extended, the restriction is the number of bits has to be greater than or equal to 43. Whereas in case of double extended, greater than or equal to 79. How many mantissa bits? Single precision, 23 mantissa bits. Double precision, 52 mantissa bits. And single extended greater than equal to 31. or here in case of double extended greater than or equal to 63. How many exponent bits? In case of single precision 8, in case of double precision 11, and in these cases these two. Exponent bias, remember here is 127, and in case of double precision 1023. So what would be the minimum exponent? Subtract 127 from 255. Okay, what would you get? Okay, you will exponent bias, you subtract. So minimum number would be minus 126, and minimum exponent in case of double precision is minus 1022. Okay, and maximum exponent is plus 127, in this case 1023. Now you can see here number of fractions, 2 to the power 23, here 2 to the power 52, and see decimal number range. In this case 10 to the power minus 38 through 10 to the power 30 plus 38. This is also a huge range, but see here it is 10 to the power minus 308 through 10 to the power plus 308. Now Python 3, which I am using under 64-bit Linux, range is 10 to the power plus 308 in 64-bit double precision floating point number. One thing remember, these crosses in red, this means this has not been specified. Now string and boolean. Internal name for string is str, and internal name for boolean is bool. Okay, we have already discussed str and bool in one of the previous videos, and remember, internal representation of bool is a boolean variable of type bool can take on values true and false. We have seen already. So true internally is represented as numerical value 1, whereas false as 0. So we should be able to make use of these bool in mathematical computation also, where only 0 and 1 numerical values are used. So this I will demonstrate in perhaps in the next video, which I would make for Python programming language. Now next one is interesting, is complex numbers. Syntax is real part plus imaginary part, then j. Normally in mathematics, I is used to represent the imaginary part, or represent imaginary part, or square root minus 1. But in electrical engineering, we have seen that the complex quantity, that is square root minus 1, is the lowercase letter I represent current, alternating current. Perhaps that is why in electrical engineering we use to represent square root minus 1 as j. So real part plus symbol imaginary part followed by j. This is the way we can represent complex number, or real part minus imaginary part j. So we use j to represent square root minus 1. So imaginary part would be associated with j, not I. Okay, so Re can be any quantity, maybe integer or a float or single precision, double precision, whatever. Okay, so in the next video, that is video lecture number 13, I will demonstrate various data types, how to read them, how to make use of them, including complex number as well. That is all in this video. Thanks for watching.